content, I'm going to start a little early. Quoting the great English philosopher and comedy team, Monty Python, and now for something completely different. Carl just took you through a 2-hour tour of everything. I'm going to take you now for a 2-hour tour of one thing. And there's going to be a difference, so where he's macro, I'm for the micro. And to do that, I need to choose what to talk about. And this was the title given me. And, turns out, I didn't realize it before until actually Carl pointed out to me. I was actually in OGC before there was an OGC. I attended a meeting in March of 1994 at Berkeley, chaired by Ken Gardells, that talked about abstract modeling. I had not realized until just was pointed out to me, this is actually a...
Sorry, so
it's not working?
It's not working. So.
That's probably because the battery's dead. No, the battery's still dead. Okay, that's okay. Sorry, I won't start over again. So, I attended a meeting in March of 1994 that was actually chaired by Ken Gardells, which turned out to the beginning of what is now referred to as the abstract model in OGC, which is a bunch of abstract specifications that define the basic concepts of how everything's put together. And we actually concentrated on the geometry. So let's talk about that. That meeting in 1994 was actually referred to as the Virtual Data Model Working Group, which later became the Virtual Data Model Working Group in OGC when they had their first meeting in July of that year. And it wrote what was then recalled the essential model for OGC geometry. And that's in 1996. That's actually the first draft of what we're going to be talking about here today, which is the geometry model, which now resides in 19107. After that, there was another paper put out talking about we weren't the only ones in the room at the time. OGC was working on a geometry model. ISO JTC1, I forget the working group number. Multimedia was working on a geometry model for SQL MM Part 3 Spatial. And ISO TC211 had also just formed, and one of the things they were going to do was start with a model for spatial schema and operators. So there were 3 of us going after exactly the same thing. And so what we did, we got really smart, and we held a harmonization meeting, which, by the way, occurred in the Oracle office in Herndon, Virginia in June, I believe, June of 1998, in which we agreed that we'd use only one spatial model and everybody would stick to the same thing. So within literally 6 months after that, the SQLMM folks, the simple feature folks, everybody rewrote everything they had done to the agreed-on common model and produced, well, simple features and SQLMM Part 3 Spatial. And just to help Carl on his history, OpenGIS Simple Feature Specification version 1.1 was published January 1st, 1999. So you were almost right.
I was almost right.
Yeah. I was surprised. I didn't know anybody be awake on January 1st. It must have been a slow year. I guess we were preparing for the millennium, which was next year. Okay, so those 2 things came out in 1999. They pretty much established what the simple version of the spatial model was. So we had basically only line strings in those things. They were mostly 2D. But in the harmonization meeting we had in the previous year, we had actually agreed on a long-term plan, sort of a gentleman's agreement. There was nothing holding us to it anywhere. We never actually even wrote it down. It was what we were going to do. And what happened is that 3 years later, after much huffing and puffing, 19107 came out, and it was the embodiment of that agreement that was actually brought forth in 1998. So it took about 5 years to. Sometimes ISO was a little slow. We knew all the answers, we just took us 5 years to get through the procedures. Now, one thing that's really strange about this, and I'm sure that Mr. Bergeroff, when he starts talking about GML, will explain what I'm talking about. What exactly is conformance to ISO 19107 is a little bit confusing for some people. It basically does not say, these are the classes, this is what you have to implement. What it says, if you implement anything that you can map to these classes in any way, you're okay. And that's exactly what GML does. And we will actually I will point this out, and I'm sure David will point some of them out if he wants to, where GML actually differs from what 19107 is all about.
Line string.
Line string is one of them, yes. Okay, and that's why I included 19136. 19136 GML, I think the original one, it was earlier than 2007, wasn't it? Remember when the first one was? I think it was earlier than that. That sounds too late. But 2.1 was the earliest one, and then there was 3.1, which I think 2007 is the 3.1 one. Anyway, so that was one of the ones that first actually included a mapping that described how 19107, the spatial schema, actually mapped to its internal implementation. Okay. Now, all this is talking about geometry models, the way geometry works in geographic space, which is slightly different than what Euclid puts forth in his postulates. So you have to be a little careful in that. And we weren't really careful enough because we took something for granted that didn't turn out to be true. Okay, but explaining this, the other pieces of it that were also discussed in that same meeting that was headed by Kim Gardels back, goes to the wrong way, that Berkeley meeting in 1994 was a concept called features and coverages. Up to that point, the general model was you had geometry and you added attributes to it. Sometimes it was referred to as a georelational model or something like that, I don't remember exactly. And we decided that really wasn't what was happening. What was really happening is there's things you're looking at, things of interest, things you're curious about that you were going to call features. So any real world or even imaginary world phenomena that you want to look at, we're going to call a feature. And some of those features have some attributes, not necessarily one, as many as you want, that somehow need geometry to describe them. So a parcel of land could have a geometry describing the parcel, could have a geometry describing the footprint of the house upon it, could have a geometry describing where the front door is, so on and so forth, the geometry describing where the utilities come in, whatever. And it's a feature, and it has multiple geometries. It not just has one representational geometry, it has as many as you need it to have. And that turned out to be really handy because that's exactly what, well, actually a lot of us were working on a DMA project at the time, and it's exactly what they needed. Actually, it goes back to 1990. The other thing we came up, and this is the one I am actually surprised, the first time this term was used was in that Gardels meeting in '98. I'm actually surprised this one survived. Coverages. A coverage is something like a feature where one of the attributes is not a simple just geometry. What it is, it's a mapping from a geometry to values. For example, if the mapping is from geometry positions to colors, you got a picture. If it's from geometry positions to elevations, you got a digital terrain model. A digital elevation model. Whatever the mapping is, it's a mapping from a geometry that's part of the feature to some value that's got a name and an interpretation. And that concept of coverages actually came up in that original '98 meeting with Gardels and folks. And it's still around. Web coverage service. The only thing we didn't do things with sensors, because sensors really sort of steps out of the wheel, because they're something looking in. They're not something in the database. They're something that looks into the database and creates it. So you can understand why we didn't sort of put sensors in the same mix. We were actually talking more about what the data was all about. So everything that was happening at that time fit the model. Everything that's been happening since has fit this model. And as far as I know, not a single primary assumption that we made in that '98 meeting has ever been broken. And that basically says the hard stuff is generally how geometry works. How geometry and how the attributes that are associated to geometry works. Now, to give you a hint, the thing we almost always use is referred to as Tobler's Law, which I'm amazed about how many people don't know what it is. Tobler I think he's still around.
He's still around.
Yeah.
Waldo.
Waldo Tobler's still around. He's a GIS guy from, I think, California somewhere.
Michigan.
Pardon?
He was in Michigan for a long time.
Okay. What he said is everything is related to everything else, but if they're closer, they're related more. And that basically says that things like indexing and whatever else makes the whole world work. One of the things that, if you look at the GIS has always been on the edge of being the largest data sets around there. When we were looking at kilobyte-sized data sets, GIS was looking at megabyte-sized data sets. When they talk about big data today, there are some GIS databases that are bigger than their big data numbers. GIS is just really big. And it's Tobler's first law of geography that allows us actually to deal with it, because it says, okay, indexing and allowing toward nearest neighbors and spatial clustering and other things that use the fact that things that are related to each other tend to be close to one another actually helps a whole lot. If we didn't have that, then the whole house of cards would fall apart. I don't know, does that mean the internet will eventually make things fall apart because it will make location irrelevant?
No, pervasive.
Pervasive, okay. I guess that's different than irrelevant, isn't it? Okay, so the real title of the presentation. The previous slides were actually added to the presentation after I did this slide. And I'm going to talk about 19107, which is the spatial schema. Now, when ISO TC211 first started, they were actually going to build two documents, one on the structural schema and one on the operations. They were also going to restrict it to 2D. So in the same amount of time, we put them both together, and we did it for up to 3D. And I was the editor. There was actually a project lead who was, I can't remember, Kim Bullock, I believe, from Australia. We never showed up to any of the meetings, but I was the editor. So I'm going to make this presentation as the editor of this thing, and possibly as the project lead for its replacement, which hopefully will come out as an INWIP, not necessarily this year, but next year. And 13 would be way too early for it to actually make international standard status. So I suspect we're looking at 14 or 15. Some things take time. Okay, that is a compressed version of the title page. International Standard ISO 19107, edition dated May 9, 2003, and the two titles, one in English and one in French. Actually, legally, the Russians can put us another one in Russian, but they always say, no, French is okay. So, that's ISO rules. ISO is actually trilingual. Okay. What the standard has in it is a conceptual schema for describing geometry, spatial aspects of geographic features. When we originally started out, we were talking map features, points, lines, areas, so on and so forth. But when we started on working on 107, we realized that eventually we'd be talking about 3D, so we didn't say areas, we said points, lines, and surfaces, and solids, so up to 3D. So we have a primitive for at least a primitive for each of the dimensions. And we have to have a set of special operators which both query the data and operate on it to give you the information you need. So that's where the operations were originally there. Okay. And this is all words from the thing. And we're embedded in a coordinate spaces up to 3 axes. And we had, and still do by the way, only 2 dependencies on other volumes in the ISO TC211 library of standards. One is 19103, conceptual schema language. Basically, it's a profile of UML. This is how you're supposed to use UML. And to be perfectly honest, GML has as good a profile, just for a different purpose. Profiles are, generally speaking, targeted towards a purpose The GML profile for geography actually targets creating XML application schemas. Is that fair, David? David shaking his head in total agreement with me. In 1.9.11, here's where the problem came in. Everybody heard of EPSG? Let's see. Yeah, I forgot what EPSG was.
European Petroleum.
Petroleum engineers. They basically have the best library of what are the coordinate reference systems there for things. They put together this lovely 1.9.11 spatial referencing by coordinates, which tells us how all these coordinates are associated to points on datums. Great. What they didn't do, and what we sort of expected to happen, was we expected 1.9.11 to talk about the underlying surface. Lat long is different if you're looking at a map, if you're looking at a sphere, if you're looking at an ellipsoid, if you're looking at a geoid. They're all slightly different. They all have different characteristics that are geometric measurements and observations. And therefore, it is totally inadequate not to tell us which datum to use or how to use the datum to calculate things like distance. So we thought that was going to actually show up, and there is sort of wishy-washy words in 1.9.107, which is targeted towards them telling us how to do this, and all they tell us how to do is how to do metadata. So that's where we fell apart. That's one of the things we need to fix in the next version. One of the things. We also have made a few mistakes. We're human, like I said. Okay, now UML1 and UML2. Actually, when we started this out, we weren't even using UML. We were using, I can't remember what it was, OMT or something? Object Modeling Technology, something by Cook and Daniels was the book. Very similar to UML. It's basically a slight variation of NVIDIA relationship modeling. So when we were moving through, if you actually, most of the, I'm glad to see Greg is actually reestablishing a lot of the archives for the earlier document. If you actually follow the geometry model through the OGC archive, you'll actually see us moving along and moving towards UML style modeling. And by the time 2003 rolls around, we were doing pretty well what we're doing. Now, what we used in 2003 was something called a stereotype called type, which is very similar to the stereotype called interface. Hopefully, most of you in here have done a little programming. You know what an interface is in Java. It's basically a description of how you access a data structure. It does not necessarily tell you what the internals of the data structure is like. Well, that's what a type is, except for in a type, you can have both protocols, function descriptions, and you can have sort of derived data that doesn't necessarily have to be there actually in the object, but has to be producible by the object. So it's sort of like a more general interface. Well, in UML1, there was a distinction between type and interface, and there was the question that an interface could not have attributes. And we really needed to talk about attributes in these things. That doesn't necessarily mean that the object has those attributes. The object has to have some way of producing those attributes on demand. Okay, now in UML2, the guys who were doing this anyway finally figured out that that was kind of silly, that why have two things when one will do. So they eventually left type alone and improved interface to allow it to do exactly the same thing as type does. So when we're using UML2, which is what we're using for the next version, all those types will wind up being interfaces. And they'll fit lovely, in a nice manner inside what most people think of as interface, like, for example, in Java or some of the other languages which use very heavily. And what's even more important, 1.9.107 relies heavily on something referred to as multiple inheritance, which most programming languages, not most, a lot of programming languages that are currently in vogue, like Java, don't like multiple inheritance. But they'll let it go for interfaces. So this is actually good for us. The fact that we're going to be using interfaces in the next version allows us to do multiple inheritance without getting screwed up. And the other things that stay the same are these two extra stereotypes called code list and union. Union, by the way, is simply data type. A code list, okay, everybody should know what enumeration is. Like Boolean enumeration is true and false. The character enumeration for, is whatever number of letters you have in the alphabet. It's a fixed set that always defines something that's going on. What a code list is a non-fixed set that has some sort of reference to tell you what's going on. So example, if you have a gazetteer that has all the names of all the cities in Korea, and if you ever want to use a reference to that city name, you don't have to type out the entire name. All you have to put in is the index into the gazetteer to tell you what the name is. That's a code list. It's an index into something else that tells you what the actual value is. Now, because of the way GML works in XML, they don't quite do it that way, but that's pretty close. Unions are actually in C++, the actual formal term is discriminated union. They're actually a fake type that becomes a super type of two things, i.e. a union is like a name or a value. You can have one or the other, either one will be fine, but it doesn't matter which one. So that's a union between those two things, and somewhere in that union it tells you what it is. Actually, you can do that in C as well. C and C++ both allow you to do that. So that's the only difference in UML. So when you see, if you do see some of the UML from the current draft of the next version of 107, you'll see interfaces, not types. And you'll see everything else pretty much stays the same in terms of what we're using in UML. Okay, now this is actually way too complex. And it's one of the reasons I really want to redo 107. First I need to tell you about the GM. The prefixes were because there was a bug in a lot of the UML programs when we first started out in 1998 is when we actually started this stuff. And it was the fact that they didn't handle namespaces very well. So we had to separate things that are in different namespaces by putting something on them that we could then control. In this case, the underbar GML. It's very similar to the prefixes that they use in XML, like OGC colon type name. It's a short handicap for a short abbreviation for something which is much larger namespace. Okay, so those will disappear in the next version because we don't need those anymore because most people have fixed that bug. That was a bug in the UML programs. It wasn't our fault. The other thing here is there's something going on which is really kind of confusing, and that's this subtyping from the composites over to the primitives. And as the primitives are sort of one for each dimension, and there's a little problem here in the middle dimensions because of orientability, which I'll explain as time goes by. So you have points, you have curves, you have surfaces, and you have solids. So there's one for each dimension if you're going to go up to 3. And then what a complex is a collection of primitives that are stitched together in some way. And if they're stitched together in some way is they look like they would look if they were a primitive, then a composite point, which is it's actually sort of silly because there really is no composite point, it's just a point, has to be a subclass of point. And a composite curve has to be a subclass of curve, and so on and so forth for surface. And there's a similar problem, which I'll show you later, when you talk about patches and segments within a surface or segments within a curve that also sort of seems to be redundant. It seems like you're talking over yourself, and that's in fact what GML did, is they took a lot of that out. When they did their own things, they sort of put segments and curves together, and they put surfaces and patches together. So a lot of this stuff is going to go away, so this entire piece right here usually may disappear. Now how that's done is actually out of scope at the moment, but we can talk about it later in the question period if you're curious about it. The other thing that's sort of complex, I'm not exactly sure we need, is this was actually put in here, the multi-point, multi-surface, multi-curve, multi-solid thing was actually put in there for the SQLNM folks. And it's totally unnecessary because the aggregate itself has a way to restrict it to a particular class, classes as members. So all these do is realize that restriction as separate classes. And this is just a lot of waste of effort and time and text. So a lot of this is going to collapse away. A lot of this parallelism between composites and primitives are going to go away, which is good because what this says here, which is really confusing to people, is that there's a composite curve, which is actually a primitive. And it confuses people because primitives in geometry do not mean non-decomposable, which is the usual definition of what a primitive is, something you cannot decompose into smaller pieces. What the actual definition in geometry is a primitive is something which you choose not to decompose. Because the only non-decomposable thing in geometry are points. Because you can always take a line and cut it in half. You got two lines. Sort of like that frog that can regenerate itself on its feet or something. Or starfish. Starfish can do that. You can actually break a starfish in 5 pieces, throw it back in the water, and you have 5 starfish. Which is really confusing to the clammers in Baltimore Bay when they tried to kill the starfish off by breaking them into pieces and throwing them back into water. They actually made the problem worse. Anyway, off topic. This is the same thing in a slightly easier to read sort of thing. Now these are just simply talking about abstractions. And they're the same abstractions that Euclid used in his postulates we described in geometry. And all of you who are taking geometry, which I assume is everybody in here, and what the equivalent of whatever high school was, is what you learn. You know, lines, points, lines, whatever. And it doesn't talk about actually how you create these things. Because when you say a curve is this set of points, you then have to describe how you get from one point to the next. How the interpolation, obviously you can't give me all the points on a curve. There are uncountably many number of points on a curve, because as I said, you can chop it in half, chop it in half, chop it in half, ad infinitum. So as many points as you want is on that curve. So obviously you can't give me all of them, so you have to tell me how the ones in between the points you do give me are calculated. Now, when we were running 107, we were dealing with basically what was a CAD-CAM mentality, which was everything was nice Euclidean geometry, and we used Cartesian coordinate systems with a nice square metric. You know, hypotenuse is the sum of the square of the hypotenuse is the sum of the squares of the two sides, sort of thing. Well, on the Earth, that don't work. That's because the Earth is curved. In fact, the way you can tell the Earth is curved is if you start at any point and go east a fixed distance, and then go north a fixed distance, the same fixed distance, and then do exactly the same thing in the other order, go north first that distance, and go east that next distance. You don't wind up in the same place. That's non-Euclidean. If you were on a flat Earth, that would wind up in the same place, which surprises me. Actually, the Greeks themselves knew that the Earth was curved a lot longer before people claim it. You know, Columbus was not discovering anything new when he discovered America. Everybody knew the Earth was curved. The only problem is they didn't know that there was this big continent there. So you should be able to actually calculate that. In fact, one of the things the consequence of the Earth's curvature is that I'm surprised that Columbus would have actually, he did know, he used one of those examples, is that as the ship sails away from you and it falls below the horizon, if the Earth were flat, it would never, there'd be no horizon for it to fall below, and it would just get smaller and smaller and disappear. But you could actually see the top of the mast and not the hull. And the only reason for that to work is the Earth is curving. And if you're good enough, you can figure out how big it is just by that alone. Okay. So there's a few points thing here. These are all the classes that we use for points. Turns out there's not very many of them. They're basically more or less things that you have to have for technical reasons. You have to be able to produce actually, the problem here is that people don't always repeat points. They'll sometimes get to a certain string of coordinates and they say, well, I've used this coordinate before, so I'll just reference the original coordinate. So that sort of thing, the ability to take an array of points and not exactly represent each one as a primitive data type, requires us to have both points and point references in the same array. So there's a lot of technical stuff you have to put together to make allow yourself to do that. And the one thing that surprises me is how people get that one wrong too. An envelope is something we use for indexing a lot. It is simply what looks like 2 points, an upper corner and a lower corner, where the upper corner is all the biggest numbers in the coordinates and the lower corner is all the smallest numbers in the coordinates. It doesn't always give you something square because the Earth isn't flat, but it does give you a way to index. In fact, the best index I know is an R star tree, and this is exactly what you use for R trees. There are some other folks who like quad trees. Sort of our tests seem to say, yeah, there's a dime's worth of differences, but it's always, to be perfectly honest, if somebody takes 2 indexes and implements them and gets less than 500% difference, then the difference is how the quality of the programmer did the implementation, not the quality of the index. I don't know why, it's a simple truth, I don't know why people don't understand that. A good programmer can get you 30% easy, can't get you 500%. Okay, and here's what I was talking about. This was the issue that we dealt with before. If we let the primitive curve be a single interpolation type, then there are a lot of things like a square box with rounded corners, which couldn't be a single curve, because you'd have to change interpolation type as you round the corner. So what we did originally was we put these things as curved segments. Every time the interpolation type changed, there was a new segment, and any particular curve could have as many of those as you want. And it's another composite going on here. And it's exactly the same sort of composite that occurs between curve and composite curve. So this is what we did then. Hopefully in the next version we'll be a little smarter. The other thing that's a little strange here is the use of special classes for boundary things. The boundary of a curve is its start point and its end point. And that's just a set of points. Why do we have to call it something special? And so this is actually just really, well, I'll admit, bad UML. If we had been smarter, we would have said the boundary of a curved segment is a pair of points, or an array of points. We wouldn't even use a collection. A lot of stuff to fix. Okay. These are the curve segmentation interpolation types we use, and some of them are probably familiar to anybody who's taken first year geometry, and some of them aren't. Linear is exactly what you think it is. It's what is on the Euclidean line. It's actually an equation which allows you to vary x and y simultaneously in a linear manner. So it's exactly what you think. There are some people who think linear and geodesic mean the same thing. They don't. Geodesics are curves of shortest distance on the real surface. Just because lines or curves of shortest distance on a flat plane doesn't mean geodesics have anything to do with lines. And in fact, the word line in English derives from the word linen. It means a rope. And ropes bend. So the fact that a straight line is actually more appropriate because it actually says a straight rope. So if you take a rope and pull it taut, it is a line. And that's where the word comes from. So in some ways there's a confusion about what the word line should actually mean. In fact, in nautical terms, a line is a rope. There are also other terms for it too, but that's okay. Circular arcs and circular arc strings, those are any sort of rounded edge which is actually a circle. Now, those actually wind up getting used quite a bit. Actually, they're used a lot in the United States for cloverleaf road patterns. The cloverleaf on the end winds up actually being a constant radius curve. So when you turn on them, doesn't matter how fast you go, you put your wheel in some place and then you go around the curve and then you straighten out. On a clothoid, which we got down here, you do something slightly different. When you start going around the curve, you start turning your wheels faster and faster and it gets tighter and tighter. So a clothoid is similar to a circular curve, except for its radius is either decreasing or increasing linearly. And they're actually better. Actually, these were first put together to get trains around corners without having them fall over. Strings have this really nasty tendency to fall over if they get too much side force on it. And they decided this is the thing to do. And elliptical arcs and strings simply because we were wanting to do things better. Circular arcs and strings, you need 3 points to determine the arc. For elliptical arcs and strings, you need 5 points. So there's a lovely comparison going on between there. You can actually get decent things. Okay. And then, just because we started this one out, we figured we'll go ahead and put conic curves. Now, if you think about all of these are assuming Euclidean geometry, which we know is not true on the surface of the Earth. So all of these are assuming Euclidean geometry within the coordinate reference system, dealing with the coordinates as if they were algebraically on a flat surface. So they have certain limitations, and a lot of them may disappear. Clothoid will not disappear, but it'll disappear in its original definition. It'll appear as a constructive definition, not as a closed form. Okay, and then we get into the stuff that are a little unusual. Polynomial splines. Has anybody ever seen a drafting spline? It's a small piece of usually elastic steel or something that has little weights on it that you can bend on your drafting board and then draw a nice smooth curve. Okay, well, I learned in calculus of variation in my first year of graduate school that physical description actually says that the curve is a cubic polynomial. So it turns out these polynomial splines are really handy to have around when you're trying to do a quick and easy, nice, smooth curve thing. In fact, tell you a little secret. PowerPoint 2010, their curves are cubic splines. I know because the way you control their shape is by adjusting their tangents, which is exactly the way cubic splines work. So if you want to see a cubic spline work, get out your PowerPoint, draw a curve, look at the points you put on it, and you'll see the two little handles on it, which are actually tangents, the backward tangent and the forward tangent. If you move those tangents up and down, the curve will bend at the point. If you keep it flat, it'll be nice and smooth. So those are cubic splines. You can do that moving up in degree to get a better level of continuity. A cubic spline gives you continuous and first derivative continuous. A quadratic spline would give you first two orders of continuity. Not only would the curve be continuous, its derivative would be continuous, and its second derivative would be continuous. And that's exactly what these things are all about. And you wind up having degrees and level of continuity defining what a polynomial spline is. The cubic spline is separated here only because it shows up in drafting a lot. Almost anything that's on a drawn picture that's not a French curve or something like that is probably a cubic spline. As I said, PowerPoint 2010 actually uses them right now. These splines are a little different. In these two things, polynomial splines and cubic splines, the curve actually goes to the point that defines it. So you get the best fitting curve that you have. A B-spline is an approximating curve. And what they do is they use Bezier curves, which there's a lovely definition for them in many books. And they approximate curves. They have a lovely set of geometric qualities that makes engineering love these guys a lot. B-splines were actually originally developed to design car bodies. B-splines and B-spline surfaces. And then rational splines are a little odd. They're like B-splines in that they start out as Bezier curves, but they start out as Bezier curves and then they divide by a common weight, and you wind up, instead of having polynomial coefficients, you wind up having rational functions, polynomial over polynomial coefficients. And these, again, are lovely because they have all sorts of lovely things that are true about them. As I think I remember the way it goes, is these B-splines are invariant under affine transformations, and I think rational splines are invariant under one level up. So when you're talking about moving from one projection to another, a rational spline in one will be pretty much the same rational spline in another. which is really handy when you're trying to do large amounts of geometry calculations and doing transformations. This may slow down a little bit. Okay, this is an example of what I was talking about. This is what a polynomial spline works like. The red line looks like a line string. It is. It's the line string that you get out of the points that you would normally get. And then the spline, and if you actually play around with, as I said, with PowerPoint 2010, you'll actually see this happen. This curve is actually defined by the points on the corners of the line string that I just drew. And that's the way a polynomial spline will look. Now, if you do play some games with them and crank up the degree, you can get odder behavior. But they generally always pass through the points that define them. So they're actually fitting splines. They fit a set of points. Approximating splines are done as curves. It turns out everything in this section depends not only on this point and this point, but it also depends on that point. And getting a larger number of points involved in it curves it around a little bit. So what happens here is that normally we go from here to here, but then the effect at this point is starting to pull it down. Now, as it moves in here, it drops the beginning point and picks up the next point, and so on and so forth. So there's some lovely theory about them, which I shan't go into, but basically they always look something like that. There is what's called sort of an underlying first-order line string that's an approximation of the original thing, and then the spline actually flows through as sort of getting pulled to one side or another by the corners of the line string. Again, they're really handy in engineering. If you're doing what is referred to as geoengineering, engineering on a scale of geography, like building Aswan Dam, putting something big, really big across a canyon, large bridge, then you have to deal with things that don't necessarily deal simply in Euclidean space. And for those things, splines are really handy. Okay. So here's what's going on, and this is just exactly the same thing that was on the previous page, except for this is now a UML diagram. And notice here the UML diagram starts with curve, which is the only primitive here, and then goes down to curve segment, and then subclasses each one. I gotta fix that. That abstract doesn't belong. Subclasses each one based on how things are working. So there's arc strings, and then there's an arc is a subclass of arc strings. So these are bunches of circles, of sections of circles. This is a single section of circle, and this is just one big section of circle. So a lot of this stuff really doesn't need to be there. It's sort of convenience. Same thing on B-splines and cubic splines. So the polynomial splines. Here's the clockwise, and no one subclasses off of clockwise. And the only difference between a geodesic string and a geodesic is this is 2 points, period. It's a shortest distance between 2 points. This is a bunch of shortest distances between 2 points of a line string, you know, think of it that way. And then this thing I didn't go into is basically a curve that's offset from one side of another curve. So it's like, for example, you have the center line of road of a particular radius, and you say the guardrail is offset from the edge of the road by 5 meters or something. That way you can define this without actually having to give it any coordinates, but it's defined by another curve, its base curve, and then the way it's offset. This actually gets used more or less in linear referencing systems. 19148 talks more about them. In fact, I probably could drop them out of here and just simply reference 19148. Probably what I'll do. Okay, this is what confuses people. And as I said it before, is the problem that in the geometry, the only thing that's really truly a primitive is a point. Therefore, when I say a primitive line, it gets confusing because every line is a primitive, even though it's a composite. So this is just sort of things how it works in terms of Here's a composite surface. It's got a generator, which is a bunch of orientable surfaces. But then this thing here is actually a superclass of that. So it's kind of odd, but that's the way it works. By the way, the idea, let me explain this. A point has no orientation. There's nothing different about a point pointing one way or the other. A curve has an orientation based on which direction it's flowing. It's got a start and an end. If you swap those two around, you're swapping the direction. And a surface has an orientation because in 3 dimensions, well actually in 2 dimensions it doesn't. In 3 dimensions it has an orientation because it has a distinction between up and down, between outside and inside. So a surface that's laying on the surface of the Earth, its up normal is always pointing outward, not into the Earth. Solid, again, since they're banging up the limitation of the dimension, do not have orientation. So if all this sort of stuff in the center where there's these orientable things are because of the ability to talk about a curve going one way or the other. And that's important because if you take a composite curve, which is a sequence of curves, you'd be really, really lucky if they're all pointing the same right direction to begin with. So you have to be able to flip them. And that's what's going on here with the orientable curve. You can flip the ones you need to flip by putting in orientation and flipping one side and leaving everything else the same. Okay, and then the curve methods. Now a lot of these are dealing with the way the construction works. The constructive parameters, so whatever you use to describe describe the interpolation. Now, what's really nice, and you can think about this for a while, the nice thing about the curves especially is that everything goes back to a line string if you want to. In other words, if I have a road which is defined beautifully as clothoids and B-spline curves and all sorts of stuff, if I get enough points, I can construct a line string which is a very, very good approximation of that curve. So one of the things that we do for all curves is allow it to produce these as line string things. What that allows you to do is to always push down to the lowest level of commonality. All you have to be able to do to read any of the data is be able to read line strings. Because what you can do is to go to each individual curve, tell them the level of accuracy you want, which is one of those distances, and it will give you a line string which is that accurate compared to that string, compared to that curve, whatever it is. It doesn't matter if it's a non-uniform rational B-spline. It will in fact give you a line string you can play, you can use. The only thing, the difference is that we lose some of the really nice differential properties of those line strings. Okay, surfaces all over again, exactly the same thing. Surface patch, surface, that's going away in the next version again because it's useless. And in fact, does GML do the same thing with surface patch that it does with line string? I don't remember. I just realized I didn't remember that for sure. I'll have to go back and think. But the same thing, they should be done the same way. And then we get into the really neat stuff here, which are the simple surfaces. The polyhedral surface is simply that. It is a surface made up of joined polygons. So the polygons are flat planar stuff with edges. So if you get a calendar, which is this strange blob with pentagonal sides and 12 sides, and each side's got 12, each side's got 5 edges, that's a dodecahedron, by the way. Dodecahedron, I mean 12-sided. Amazing, isn't it? Dodecahedron is a polyhedral surface. And if you break those things down and down, finer and finer triangles, you get a triangulated surface, which is exactly the same thing as a polyhedral surface, except for all the polyhedrons are triangles. And triangulated surfaces, triangulated ruler networks, for example, are very handy in things like digital elevation models. But they're also very handy in doing rough general calculations on things that are a little harder to deal with if they're in sort of a more abstract form. In fact, I'm surprised how good some of the triangulated surface renditions are in graphics. They really look almost real. They just sort of look kind of shaky. And to those, we add, this is out of order. Oh, no, it's not. To those, the polyhedrons, which we started about, these things are a little weird. They're, you know what a ruled surface is? A ruled surface is something you can take a bunch of lines and then sort of move them and twist them and produce a surface. It's called a ruled surface because every particular cross sections of the surface are actually straight lines, always straight lines. So a conic section is a ruled surface. It's basically what sweeps out as a line moves around in a circle. A lot of stuff is ruled surface. A lot of things that don't even look like they're ruled surfaces are ruled surfaces. Well, if you generalize that up and let sort of those parametric curves be any grid spanned by a defined set of polynomials, you get some really lovely things. Biquadratic, bicubic grids work very well in digital elevation modeling. And they're actually fairly easy to calculate and play with. And then once you've done that, you can move on to polynomial splines and rational splines and things like that. And this one actually I don't think anybody's ever done. Triangulated splines was actually set up and done in the 1950s, I think Renault, in defining car bodies, but I don't think anybody's ever used them in GIS. We sort of given a reference in the 107 because we never know when somebody might want to use one. Okay, now, luckily we ran out of dimensions. Solids don't need special casing. They don't need special interpolations because they're all defined by their boundaries. It's called boundary rep. So if you want to talk about anything, all you really have to do is tell me what the solid's boundary is. I know everything you know. Now there are reasons why you might want to go one step further and actually talk about ruled solids or whatever, things where there's curves inside. They will give you a way to reference the inside of the solid using these parameters. But that's something beyond the scope of what 103 was about. So this is the easy one. And where polynomials, surfaces have rings that traverse their boundaries, solids have shells. A shell is simply a closed surface that either describes the exterior surface of the boundary or the interior surface of a hole inside the boundary. Of a hole inside the solid plane. Okay, obviously, we have to play little games here. Solids are obviously not available in a 2D CRS. Doesn't make any sense. Now, a lot of 2D CRSs are extended to 3D by giving you an elevation. The problem is the elevation axes are not parallel to one another because the Earth is curved. So as you move up, you don't preserve distances. So there's a lot of really nasty CRS stuff going on here that was not covered by the original 107 because we thought 111 was going to take care of it for us, so the people that we were, they would have to take care of in the new 107. And again, in 3D, solids are defined by their boundary representation, i.e. all the boundary surfaces, with all the normals always pointing outward. This is the solid equivalent of the boundary of a surface always having the boundary to the left of the surface. It's that orientation thing that if you look at it from above, it's always going counterclockwise on the outside, clockwise on the inside. This is just the equivalent in 3D. Well, I haven't got to the good part yet. We need an entire hour for topology. Okay. Well, I sort of got this thing. A complex is a collection of primitives that are knit together by having common boundaries. So if you want to think about a donut, torus, which is basically this sort of circle that goes around in a circle, then you slice it straight through, you basically have two surfaces, an upper and a lower one that you can together. So that becomes a geometric complex. Something so that all the boundaries of the things in the thing are still in the thing, so there's no edge to come to, and you wind up having a complete thing. And this is setting this up. And it turns out that this gets used more in topology than it does in geometry, because of the way topology works. We actually need topological complexes which have to be underlaid by a geometry which has to be a geometric complex. So we're actually getting into that edge. And this is the same picture from before, except for now, instead of dealing with, well, actually it is the same picture before, isn't it? Take that back. No, I don't know why I put this one in there twice. Well, slightly different layout, but the same picture. Okay, let's start talking about topology. Okay, any questions about geometry at the moment? You got the light so I can use raise a hand. Any questions anyone wants to bring up? I got plenty of time. I'm not tired. Nor Brad. Okay. Topology. Topology is actually what I got my PhD in. That's why I like it so much. As we go around and make house calls. It's a doctor. And besides that, what topology is, it's a way to study things that are invariant about geometry, invariant under continuous transformation. So if you bend, stretch, whatever, do anything but break a piece of geometry, then things which are topologically true are always topologically true. If you take a map projection, if you have a city inside of a county and you project it onto a map, then the city is still inside the county, as long as that's what you did on the map. And that's because the mapping is continuous. It's a projection. It's a geometrically defined map. So when we start talking about things which are invariant under continuous transformations, we start talking about things that we see and perceive, but don't necessarily have any way to measure physically using distances and the like that would tell you what's going on. And that's what this is about. And what you do in topology, and generally algebra, it's called algebraic topology. What you do is you break geometry up into primitives, points, lines, and areas, where the primitives no longer contain their own boundaries. So in the original geometry, a line always contained its endpoints. In topology, the corresponding thing to a line is an edge. It touches the corresponding thing to a point called a node, only two places, at its beginning and at its end. And it doesn't contain those points. So a circle, if you pick a node on it somewhere, it becomes an edge with a start node and end node being the same thing. Okay, and a surface has edges along its boundaries, interspersed with nodes, of course. And on each edge, if you traverse the edge in which the boundary describes it, you always have the surface on your left. Okay, now, what I described is, it's very, if you draw pictures, it's really easy, but I would take us an hour to get some pictures. So what I have is these nodes, edges, faces, so node, edges, faces, solids. They're all pieces of the complex, and for convenience, I subtext them with their dimension. And the nice thing about it is that the boundary map moves down this tree. The boundary of a solid is always a bunch of surfaces. The boundary of a surface is always a bunch of curves. The boundary of a curve is always a bunch of points. The boundary of a bunch of points is always empty. Now, what you then do, and I apologize for the thing, this phrase, because I'm going to have to explain it anyway, you then create free groups on these things. Now, what a free group is each one of these things has a symbol associated to it, like edge number 37, whatever else. what a free group is you treat each one of those representational symbols as a variable and a polynomial. And you do all your multiplications and polynomials like that. So a lot of stuff you'll see will look like polynomial equations. What they're doing is they're manipulating these objects and their boundary operations as if they were polynomials. And it turns out, if we start with, let's say, if you start with a sphere and take its boundary, no matter the way you decompose the sphere, it will always give you 0 as its boundary, because it's what we refer to as a closed surface cycle. Now, if you take just the surface of the sphere, if you take the interior of the sphere and take its boundary, you'll always get the closed sphere. So there's some things that fill in the hole that's inside the surface, which are the solids. Now, what topology knows is that anytime there's a hole in something in a particular dimension, one of those things doesn't show up. So there's something which is a cycle, is a closure, but for which there's nothing filling in the hole. So, for example, on the surface of the torus, there's actually two things like that. There's a circle that goes around the torus, around the vertical perimeter, and there's a circle that goes around, and it turns out those are the only two. Everything else is related to one another simply by a continuous transformation. So what's going on here is when these cells are considered as open, not the boundary, and each one is always in only one cell or complex, this is setting up what's going to happen next. Now, this is a long story too. I don't know when to tell it or not, but here we go. Okay, this is exactly what I just talked about. This is the setup for all what I just said, that everything's acting like it's a polynomial. Okay, this is just a picture to explain to you what's going on. So here is the geometry of something. It's a surface, and it's got an interior and a boundary. The interior is the yellow part of it, and the boundary is the thing that's on the edge. Each one of those is in turn itself a complex. Same thing with a curve. Here's a curve that has a boundary and an interior. In points, the boundary is always empty, and the interior is always itself. We're getting there, believe me. Okay, now what's going on is that the topological objects always sort of tend to associate something which is a topological term. The topological objects have exactly the same structure that the geometric objects do. They parallel one another. The only difference is these things are restricted to that sort of general underlying realization as geometry that I just described. They have to be disjoint. They cannot contain their boundary, whereas geometry is the other way around. They can be as non-disjoint as they want, and they always contain their boundary. And here's what is happening underneath. These are the actual pieces of topology, the actual node, the actual edge. These are the directed versions of them. So each face will have two directed faces, one positive, one negative. And unlike in geometry, each solid will have two. That's because these are actually going to work like variables in a giant polynomial. And that giant polynomial, if you read the standard, is called a TP expression. Okay, what are we building to? This is talking about the geometric association between the topology and the geometry and how it works. Right yet. Here's what's happening in geometry, which we talked about earlier. And here's exactly what's happening in topology. Exactly the same thing in both places. What we're building here is sometimes called a categorical functor. Here's a space with a bunch of objects in it that do something particular. And here's another space with a bunch of objects that do something very, very similar. And what we're going to do is we're going to take a problem from here and turn it into a problem in here. And because we have nice, easy combinatorials to deal with here and really nasty geometric calculations to deal with here, it will turn out that the problem is easy to solve up here, where it's not so easy to solve here. give you an example. When I was taking my topology qualifying exam, there was a test question, swear to you, about combing the hairs on a billiard ball. What it says is that if you have a ball and you have a vector at every point on the ball, like a hair, that's tangent to the vector, and it's a continuous tangent space, is that possible? And the answer is no. Now the mathematical proof of the answer is no took about 100 years to figure out, and it is literally about 80 pages long. The topological proof, which I shall not reproduce here, is 3 lines. Because what it did is it changed all that nasty computational mathematics into a couple few algebraic equations. And this is just setting up exactly the same thing about how the way the boundary and the co-boundary works. The boundaries all go down in dimension. So here's the solid, its boundary is a bunch of faces. Here's a face, its boundary is a bunch of curves, so on and so forth. Oops, Vegas. And the co-boundary is exactly the opposite. Here's the face, here's its co-boundary is a bunch of solids. These are the solids whose have this face on their boundaries. So if you're talking about an edge and you say what are the 2 faces adjacent to the edge, you're talking about the co-boundary operator, going from the edge to things whose boundary contains the edge. And when you're talking about, let's say, a curve, and you say where does it start, where does it end, you're talking about the boundary of the curve. So they're talking about boundary operators. Okay, here's where the stuff hits the fan. I assure you Max had absolutely no topology behind him when he did this or not, when he did this. He was actually a grad student in geography, in geographic information science at University of Maine under Andrew Frank, who is now, as far as I know, still at the University of Maine. And he wrote, and this is his, by the way, Max is now, this is actually something unusual about Max. He's actually a professor at the school that graduated him, which is almost never true. You almost always have to change school when you graduate. He actually became a professor at the University of Maine. So Max is still at Maine, and he has collected a very lovely list of his publications. If you go in there and follow the word topology, you'll get a couple hundred books, you'll get very many descriptions of what's going on, none of which, by the way, have topology in them. And if you do him on sites here, which everybody should know how to use, you'll find everybody else who's talked about it, including Eliseo Clementini, who was the other person in this who's done a lot. But Max's idea was this. I have 2 pieces of geometry. I want to, actually, he started out with 2 surfaces. I have 2 areas, and I wanted to describe some way what their topological relationship is. So I look at the topological interior and boundary of the areas, and I intersect them. So I have a 4x4 matrix, 2 interiors, 2 boundaries that give you interior, interior, boundary, boundary, interior, boundary, boundary, interior. You get a 4 matrix, and then I characterize those sets. Are they empty, not empty, whatever. That gives me a characterization of that relationship. Any other pair that had the same characterization should look pretty much the same. So that's what he did. And then after he did it once, he did it again, saying, okay, that's not quite all I want to do. Let's go a little nastier and go to 3. Now, the 3 operators he uses is interior, boundary, which is sort of the partial derivative sign I'm using, and exterior. So if you think about it, the interior of A, the boundary of A, and the exterior of A basically fill up the entire space. So, for example, this guy right here has all 3 of the pieces of B. So if you were to union this thing all the way across, you would get exterior A, because that's the only thing that's common here. So this is exterior of A intersected with the universe. So the union of all 3 of these is exterior of A, but they're totally disjoint. And it's the same thing for columns. All all of these has the exterior B common in them, and they have all three of the possibilities for A. Put these together, union them, and you'll get exterior B. Here you'll get, union all three of these together, you'll get the interior B. So there's some really nice checks on these things and restrictions about the way they're going to look, so you can actually look at them. I think that's what I did next. So the idea is to begin with two geometries, doesn't matter what they are. By the way, it would be better if they were composites. There are problems with non-composite geometries which still have not been solved. And in fact, we're still arguing about them. Take two composite geometries, represent them in a topological complex. That means divide everything up into its primitive pieces so that you have a finite set of edges, a finite set of nodes, a finite set of faces, and the union of all of those is the entire space. You apply the 9 operator matrix, i.e. those things I just did on the previous screen. You apply those, and that gives you a matrix of sets. And then taking those, you categorize those sets in some manner. Now, Max's first paper used this one. Those things are empty and not empty, and he was only using a 4x4, not a 3x3. Clementini did these things, and he used the 3x3, so he called it dimensionally extension 9 intersection method. Which is a long. This is Eliseo Clementini. 107 has both of these in it. But as long as you have a characterization that you want to use, you can do exactly the same thing they did, it just to be more finer and finer. In fact, a lot of the stuff that's actually done is done that way because they don't actually do the characterization. They do it. They say stuff in English as opposed to in mathematics, which is, I suppose, okay. It's the same thing. And these are actually the two systems that are set up in 19107. And there's nothing so irritating. It's a good example. Here we go. Okay, here's an area and a curve sitting in the universe all by themselves. Okay, so let's start thinking about, well, how many edges are there? There's a whole bunch, actually. There's the line, but it keeps on crossing other lines. So every time it crosses another line, you have to put a node in there to break it. Because an edge can only have one face on its left, one face on its right. So this nice curvy line is one edge till it hits the yellow thing, then it breaks a node there, then it's one edge till it hits the other side, breaks a node there, then it's one edge till it hits the side again, breaks, another node, another break, and then the final edge. So that first line has got 1, 2, 3, 4, 1, 2, 3, 4, 5 edges in it. There are there are 5 edges, there's got to be, let's see, 6 nodes. 1, 2, 3, 4, 5, 6, yeah. Because there's got to be a node on either end and it doesn't wrap around. If it were a closed curve, it would have exactly the same number of edges as this node. So, let's look at the interior of A. So A is the yellow area. The interior area is the yellow thing. The boundary of B, the interior of B is anything except for the 2 nodes on the ends. So if the interior A and the interior B, they give you 2 edges. And the 2 things that cross the the 2 lines that cross the yellow. So that's 2 edges right here. The boundary of A is the boundary of that yellow thing. The interior B is that curve that crosses it. So if you intersect those things, you get 1, 2, 3, 4 nodes. And what's left turns out to be 3 edges. And if you add these things up together, you get 5 edges and 4 nodes. That's not right. Oh, yeah. Okay. Yeah, the interior of B is 5 edges, 1, 2, 3, 4, 5. It doesn't contain the 2 nodes of the end. That's where I lost the 2. Sorry. So the arithmetic is right. So if you actually go through this is what you get. I don't know what I ever want to show. So that tells you what things are, and then you apply your things. if you're doing Ingenhofer empty, not empty, then you have two empty guys right here, and everybody else is not empty. If you're doing Clementini, this is dimension 1, this is dimension 0, this is dimension 1, this is dimension 0, that's dimension 2, 1, and 2 again, and these are dimensionless empty. So you can actually calculate either the Ingenhofer matrix or the Clementini matrix fairly strictly, just from the picture. And if you want to call that process, you figure out which one of those are important to you. And that's exactly what happens with simple features. They actually give names to the patterns by taking an example like this, deciding, well, that's going to be processed. What part of that picture is important to me to be processed? And you make the decision. It's got to make something like this true. Okay. Now, this is sort of a wind-up slide here. The thing we're going to do for the next edition of 107 is we're going to do the simplifying of geometry spaces, so I don't have to worry about everything being Euclidean. So I'm going to work on globes are represented by either spheres, ellipsoids, or possibly geoids, and I'll continue to use maps for things like engineering systems. For example, if you're building a large building, you have an engineering system because the guy doesn't, he just sticks a stake in the ground and measures from that. And as long as you know where that stake is and which way his axis is, like, you can actually calculate out what the geographic coordinates are. That problem about the arc of a geoid getting longer as you go farther and farther up in altitude, turns out that's really not important to cars, but airplanes have a problem with that because they go up more than cars do. So we have to describe how that's going to happen. There's already a change request out there to include other spirals in common use other than clockwise. There's a problem in the way we actually did the NURBS. There's an error that's been known for a while, and we'll have to correct it. And then we have to sync with it. See, we're sitting here in this sort of environment where we started out in sync with SQLMM. And it's been 10 years since we did this. So SQLMM has done some other stuff that we have to sync up with. So we're going to go out, and basically most of the things are things like a couple of these and things like pins. You have to make sure. And then what we need to do is something which is actually pure OGC. And OGC, as far as I know, is the only one doing this sort of thing, which is we're describing how the standards are being written so that they're easier to decide when you're conforming or not. And for if you're curious about what that is, there's the OGC reference number, and it's on the public page. I have pointed that one too. That's a beautiful piece. And I say so in my honest. Questions? Well, that's pretty good. I came out of that. Any questions? Comments? Diatribes? Complaints? Yes, John.
Probably people might be interested in how those beautiful geometry models are implied in OGC and Oracle Spatial.
Yeah, they are. It's really kind of strange because GML uses a typing system which is derived from the XML, so they had to get rid of the multiple inheritance. So they did one thing. We actually don't use a typing system. We use a data system, which essentially has defined a single flat data structure which can hold anything. And that's the way it's done in Oracle Spatial. It's very, it's kind of has, there's no easy explanation, but it's actually fairly easy to do. All that documentation is online. You don't have to buy Oracle to get the documentation. All you got to do is Google it.
Another question is, on Friday we will have a workshop between GIS and BIM communities. Joint workshop on GIS BIM.
Oh, BIM.
Yeah,
Building
building
information
information model.
Yeah, okay.
They use a lot of, they all from the old computer-aided design communities. I mean, building information model. I see the geometry models are all also essence of those building information models already.
Well, they're not.
Do you see any issues or easiness, difficulties?
Generally speaking, no, because we both grew up in the same environment of CAD/CAM and whatever else, and all the stuff I've talked about here today. The newest thing in this presentation is MERS, and it dates back to the 1950s. So all these guys that have all this background in place since the 1950s to build their systems, and it's all the same thing. So they should not be able to go too much awry because of the freedom expressed in the conformance class way that 107 works. And if you look at GML, and I'm sure Dave will talk about it after lunch, right? About the way GML is put together, they actually used a lot of that flexibility in the way this is done. All they have to do is tell us how we get from GML to whatever else. So, for example, if Carl was talking about GML, KML, when they built those transits from one to the other and back, they didn't have to do a lot because they were basically dealing with the same concepts as geometry. Now, I don't know if they read 107 or if they read Simple Features or if they read SQLM. They're all the same everywhere.
JSON also uses 107.
Yeah. It really worked out. If you look at the early history, it's actually amazing that we managed to do that in a short period of time as we did do it. Considering that for the first year, we weren't even an organization. Questions? Yes, sir.
So yes. Once I have talked with some guys from robot,
Okay.
and they are using some model for three-dimensional object by means of oak tree, or for two-dimensional object they are using a quatrain. So is it possible to represent this kind of oak tree or quatrain by means of?
Quadtrees and octrees are normal in the way we do things. Are indexes you put on things.
Yeah.
They're not actually part of the thing. Now there are some. Oh shoot, what's the best name? Hanasama. Hanasama wrote a lot of stuff on how to use those to actually create models, but they have certain tessellation issues. If you create models out of octrees and quadtrees and all your surfaces are on the edge boundaries of the trees, and they look very blocky. It's the same sort of irregularity you see in a triangulated neural network. Yeah, you can do it that way, but it's not necessarily. Sticking back to the classical geometry is fine. I mean, most of the stuff we're talking about was together by 1903. The only thing that dates back beyond 1903 were the splines. In fact, only the rational splines date beyond 1903. All the others were actually in place for 100 years. All I have to do is make sure we all have them in the same. Okay. Yes, sir.
Oracle supports topology data model and network data model. Oracle Spatial supports implementation of network data model and topology data model.
Yes.
If we have got feature data tables ready, is it possible to create topology in Oracle Spatial? Like
Yeah.
there is a road feature table ready. Can we create road network data out of this feature data?
Okay, there's been a long-standing argument in GIS about which way you do this. The answer to your question is yes, but you have to play around with the inaccuracies in your data. Obviously, if two roads cross one another and one was digitized by one guy and one was digitized by another guy, then you cannot necessarily assure yourself that they actually physically cross in the data set because somebody may have made a mistake. So, for example, in Cincinnati, there is this huge flat wall that separates a interstate highway from a residential area with houses in it. And the road in 2D comes directly up against the vertical partition wall, and actually on the map looks like it touches the highway, but you know it doesn't. So there's that sort of things. There are errors inherent in the data that you can't predict, that sometimes you may have to go back and have somebody look at to figure out what's going on. So yes, you can do it. When I was playing an intergraph, I started out this whole thing as an intergraph employee. When we were playing around an intergraph, we had two different ways of doing it, which were, one is build the topology as we were doing the digitization, and the other was after the fact. And to be perfectly honest, the one that we did it during the digitization and continually kept up at all times was faster and more accurate and less of a hassle than the on-demand. And the way Oracle Spatial works now is it's up to you which way you want to do it, because there are arguments both ways. I think the arguments to the on-demand are fallacious, but that's just me. So there's always business cases. The multiple sources of data is always a problem.
But it's possible to create the network table on the topology table.
It's always possible to create the topology table, but if you have junk spaghetti coming in, you're going to get junk topology.
That's a data entry problem.
Yes, that's a quality problem, and there's just nothing you can do about it. Hopefully, as GPS gets better and more data comes from this GPS, we'll have less of a problem with that, but it will probably never go away. Again, that example of the wall, literally 3 inches of brick separate this road from this interstate. Well, 3 inches of brick in a 20-foot drop. So if you're doing it in 2D, you're screwed. Do it in 3D. Other questions? Yes, sir.
Hi, John. You mentioned that you're working on rewriting 107.
Yep.
And it might be helpful for us to understand the backward compatibility problem. Existing 107, a lot of systems, spatial schema being so fundamental standard that rewriting the standard might impact some of the existing systems?
Well, one of the first things it's going to say in the new edition is that anything compliant with the old edition is compliant with this one. And then we're going to work really hard to make that true. Because there are obviously two things going on. One is the old edition has certain requirements in it that you read and you can determine. And the new one says something similar to it, and you want to make sure those align. Now, the issue basically is going to come down is that spatial schema does not depend on a particular object model. It depends on being able to map one object model to another. That's why GML, even though it doesn't use curve segments the way everybody else, the way 107 uses it, I almost said everybody else, but that's not true. Doesn't use curve segments the way it is. It's still compliant with 107 because in the back of 19136, there's a nice little section that says this is the way the mapping works. And that turns out to be what geometry is geometry. Any model of geometry should be mappable to any model of geometry. All that 107 is going to require is that you be able to tell us how that mapping works. So the new 107 and the old 107 will fit together easily because they're both using the same set of paradigms. If there's Cedrus or something else out there, which is another geometry model altogether, it should still be able to fit together because geometry satisfies certain rules that force you to do certain things, and as long as those rules apply, they should match. That's kind of theoretical, isn't it? Yeah. It's true, though. Other question?
Well, I think that's a kind of mandatory or optional kind of issues. I mean, for example, A group is utilizing certain set of geometry mandatory, and B group is saying another set of geometry element mandatory, and
yeah,
both.
I don't think those are talking about different geometries. I think they're talking about different visions of the same object.
Yeah.
It's like projecting something from vertically or horizontally. You get different projections. You get different shadows of the lights coming from the side or from the top. And ergo, you going to get different views. They're not going to look like the same thing, but it's only a case of perspective, not the case of the way the geometry is represented. Okay, other questions?
John, when do you expect to start putting a new work item proposal for 19.1?
We started about 6 weeks ago, and we're having some meetings this meeting. We've already started.
Yeah.
And you know pretty much what's going to go on. The hardest part is backfitting 19111, because we still have to use the CRSs from 19111, but I have to backfit them in to accommodate indicating which surface they're going to be using on it. Because give you a terrible example, the KML-GML problem. KML uses WGS84 coordinates, but it uses an underlying sphere to actually do their geometric calculations. Okay, now it turns out that that's not really bad. They don't make they don't get terrible mistakes about it, especially if they restrict themselves to small locales. GML uses WGS84, uses an underlying ellipsoid, which is not the same as a sphere. And therefore, if somebody were using GML the way they should be using GML and using the datum for WGS84 and not some approximating sphere, they're going to get different answers. So that's the bad part. We need to be able to advertise that the guy who's using GML and using the right datum and that guy using KML and using the wrong datum are going to get different answers. So they have to be able to advertise what the hell they're doing so we can know that a priori and not have to go, oh crap, why are these different places? And it's not trivial. It could be quite bad in terms of the error, unless you're dropping nuclear bombs and doing them there.
So you're expecting something out to the community, what,
probably some part of next year. I don't know what it is going to be, but the people who were really obstructing it sort of disappeared because we sort of got a bit of around it all parts, and all we have to do is decide not what to do, but how to do it. If you're a member of OGC, sign up to the Simple Features SWG, and you will get all this stuff pouring through your mail every day. Okay, anything else? Okay, you got to announce lunch now?
Okay, thank you for the asking. And thank you.